Hello guys, welcome to Self Help Maths Academy. Today we are going to talk about the derivatives. So now first let us try to understand what is the derivative of a function at a point. So derivative of a function at a point. What is the derivative of a function at a point? So here if I have, let's say f is a function from the closed interval ab to r. So it's a real valued function. Let it be a function. It's a function. And say C is any point in the open interval AB. Then F is said to be derivable or differentiable. We also call it as differentiable at the point C if limit f of x minus f of c upon x minus c as x is tending to c exist. In other words, we also write the same thing as, or we will write this as limit of, wherever x is there, I'll put c plus h minus f of c upon, this will be as c plus h, this one, c plus h minus c, that will give you h here, as h tends to 0. Okay, let me explain this. So here, basically, the derivative of a function at a given point will be a function from the closed interval AB to R. So basically, you have a function from the closed interval AB. This is, say, for example, on the real line, if you're taking a closed interval AB to R, this is the it's a function. Let f is a function from the closed interval AB to R. So we are considering any point, say C, in the open interval. I'm taking any point C which belongs to this open interval AB. Then our function f is said to be derivable at this point. When the limit of f of x, the given function f at a point x and the given function f at a point the c. Okay, so it is basically, if you observe, it is the rate of change. Okay, so instantaneous rate of change we are trying to discuss. So here what happens is, we are taking f of x minus f of c divided by x minus c as our x tends to c if this limit exists. Okay, in other words, when I change our x by x plus h, x by c plus h, if I put x as c plus h, then this quantity will change to f of c plus h, as you can see, and f of c as it is. So here it will be x, we are changing it to c plus h, so this will become c plus h minus c. So c cancels, we will get h here. That's the denominator. And as you know, as your x tends to c, what about your h tends to b? Whenever x is tending to c, just substitute wherever x is there c, we put c. This is equal to c plus h. We can cancel this c. So therefore h will be what? 0. That means what? As x is tending to c, it implies your x is tending to 0. Okay. So what in a shorter meaning, the limit, if this limit exists, or in other words this limit exists, then we say that the given function f is derivable or differentiable at a point C. Okay, so this is the important definition. So limit in this case, when I say it is exists, is called derivative or the differential coefficient of the function at x equal to c. And usually we denote our differentiation by f prime of c, or we can also read it as f dash of c. Okay, so this is the notation for our derivative. So here let's see now what is the left derivative. Left derivative, as you have left limit and right limit, right hand limit and left hand limit, we have here left derivative and right derivative. So same, we have a function f is a function from the closed interval ab to r. It is a function, and let c be a point in the open interval ab. If here, if limit of f of x minus f of c divided by x minus c as x tends to c minus, okay, from left hand side, or in other words, change your x by c minus h, c minus h. So this is your f of c divided by, here as you write c minus h, this will become what? A negative h. So here limit should be as h tends to 0 plus, okay. So if this exists, okay, if this exists, then this limit is called left hand derivative. This is called as left hand derivative of f at a point c. And usually we denote our left hand derivative by f dash of c minus 0, or we also can denote it by f prime of c minus, okay, we can denote this way, or also we can denote it as left derivative L f dash of c. So these are the notations for our left hand derivative. Okay, similarly we can also define our right derivative or right hand derivative by for this also we will take the same procedure. Let f is a function from the closed interval ab to r, and let c be any point in the open interval ab. Okay, then here what we say, here we say that if our limit, if the limit f of x minus f of c divided by x minus c as say x tends to c plus, x tends to c plus, or you can also write it as say limit of, instead of here x plus c plus h, we will take here, sorry, c minus h, we will take here c plus h minus f of c divided by, when you put your x as c plus h, it will be h here, and then this will be h tends to 0. So either this or this, it is fine, both are same, it exists. Then we say that it is right derivative, right hand derivative of function f at c. So here also we usually denote it by either f dash of c plus 0, f dash of c plus 0, or we can denote it as f dash of c plus, or we can also denote it as r of f dash of c or r prime of c. Okay, so this we can denote it with our right hand derivative. All right, now let's see next thing is, when we want a derivative the derivability in an interval, how do we define derivability in interval? In interval, how do we define this? So here basically we will take a function, say f from the closed interval ab to r, okay, is said to be derivable in the open interval, ab if f prime of c exists for each c such that A is less than C, which is less than B. So basically, when we say that it is derivable in an open interval AB, that means your f dash should exist. This derivative should exist for every point in the open interval. So for each and every point in the open interval, at every point where C may be any point in the open interval AB, if your derivative exists for each and every point in this interval, then we say that the given function f is derivable in the open interval. Okay, so in other words, the same thing we can say for a closed interval. Like for example, a function f is from A to B, say AB to R. This is said to be derivable in the closed interval. In the closed interval AB, closed interval AB, when if the first condition is your f dash of C exists, your derivative f dash of C exists for each point, for each point C belongs to the open interval AB, first point. Second one is the right hand derivative f dash at the point A should exist. So the right hand derivative at a point A, because it's a closed interval, right hand derivative at a point A should exist. And the third point is the left hand derivative at a point B must exist. So here in the open interval, what happened? We have to take each and every point in the open interval AB. But for a closed interval, f dash of C must exist for every interval, open interval AB. Okay, so where C is any point in the open interval AB. Second thing is your right hand derivative should exist at a point A. So right hand derivative should exist at a point A and left hand derivative must exist at a point B. If these three conditions are satisfied, then we say that a given function f from A to, say f from the interval I to R, f from the closed interval AB to R exists. F from the closed interval AB to R exist. Okay, closed interval AB to R exists. That is the difference between the open and the closed interval. And similarly, the same function from any interval, say f is a function from any interval I to R, it is, we say that it is exist or it is derivable on I when if f is derivable at every point of I. If f is derivable at every point of I, then we say that the function is derivable on I. Okay, so this is another thing. So what is basically we are trying to understand is, we are actually trying to understand here from the the derivative of a function at a point, when we say it is differentiable, and left hand derivative at a point, right hand derivative at a point, and then in the interval when we say that the given function is derivable or the derivative exists in the open interval and in the closed interval, also for in general any interval I. Okay, so these are the some of the concept we should know. Now let us try to understand one particular property which is very important, that the how do we connect the derivability and continuity. Okay, what is the connection between them, whether every differentiable function is continuous or every continuous function is differentiable, which one is true, which converse is not true, all this discussion we will see here. So for this we will first try to understand one basic important theorem. So it says, it actually connect both the properties. What it says is, if a function is derivable, if a function is derivable at a point at a point, at a point, then it is continuous, then it is continuous at that point, at that point. So this particular theorem, it says, it's very important theorem, a basic property which explains if a function is derivable at a point, then it is continuous at that point. Means if the function is differentiable, then it is continuous. That's the meaning. We will see whether the converse is true or not true. All that discussion we will see once we done with the proof. So let's prove this. How do we say that a given function is if it is derivable, whether it how we prove that it is continuous also. So now let's start with the given hypothesis. It is given that let f be a function, let f be derivable at say x equal to a. Okay, then we know that a given function is derivable at a point only when if limit of f of x minus f at the point of a, because at a we are taking, so I'm taking, instead of c here I'm taking a, divided by x minus a as x is tending to a should exist. By the definition of a given function is derivable at a point and is f dash of a or f prime of a. This is also denoted by f prime of a. So now what we do, now I will consider, let me take f of x minus f of a. F of x minus f of a. I mean, like, what I'll do is I'll actually try to consider this f of x minus f of a. I'll write here this same f of x minus f of a as f of x minus f of a. I'll multiply and divide with x minus a. There is no problem. If I multiply and divide with x minus a, this cancels, it is still f of x minus f of a. And here clearly x is not equal to a. So therefore, now what I'll do, I'll take a limit on both the side. Let me take a limit as x is tending to a on both the side. So this is limit of f of x minus f of a. This is also equal to limit of f of x minus f of a divided by x minus a into, this is x minus a here, as x is tending to a. Okay, so this is what we have got. Now this is equal to, I can write this, I'll just separate a limit. Like if you see, this is if I consider this as say some one function and this as another function, it is limit of f and g, then we can write it as separate limits. So by using that property, I'll write this as limit of f of x minus f of a divided by x minus a. This is 1 as x is tending to a here. Then this is the limit x minus a as x tending to a. And this one is as it is. Like this one, I can write this as limit. Here if you see, this is like limit of f minus g. So I can separate the limits here also if I want. This is limit of f of x minus limit f of a as x is tending to a. So this is equal to, if you observe this particular this particular entity, this is it not by the definition of the derivative at a point. So this is nothing but f dash of f prime of a. So this I can write it as f prime of a. This quantity is my f prime of a, and this one, if you see, this is limit as x tends to a. Wherever x is there, if I put a, it is a minus a, which is 0. This will give me 0. And on the other hand, I have here limit of f of x as x is tending to a. This is limit of f of a as x is tending to a. Okay. So now if you see on the right hand side, anything into 0 will be what? This will be 0. And here what I do, here this let me take f of x as x is tending to a minus limit of f of a as x is tending to a. So I'll take this entity on the other hand. So this I will be getting as limit of f of x as x is tending to a is equal to limit of f of a as x is tending to a. So as you know, limit of f of a as x tending to a means this actually entity is free from x. So it is simply what? This is simply f of a. This is simply f of a. This is equal to limit of f of x as x is tending to a is equal to f of a. If you remember, this is nothing but what? This is nothing but since your f of a is nothing but like this is one of the property of the continuity which we have discussed. So therefore, if you want, you can write here, since f of a is constant, f of a is constant. So therefore, if you see, therefore this is nothing but a definition of what? Continuous function. So therefore, what we say? F is continuous. You know that the given function is continuous at a given point only when limit of that function as extend to that point should be equal to f of that point, right? So this is the property of a continuity. Hence we say f is continuous at a point A. So hence we started with f is differentiable. We started with f is differentiable or derivable at a point A, and now we concluded that f is continuous at x equal to A. So hence the theorem says what? Hence derivability or differentiability at a point implies what? Implies continuity at that point. This is very important proof. Now we proved it. Now the next important question is the converse of this theorem is true? Is the converse means when if the function is continuous, is it differentiable? Now we say if the function is derivable at a point, we say it is continuous. But if the function is continuous at a point, is it give the validation for the derivability? The answer is need not to be true. So here the answer, like let us say that the converse of this theorem need not be true. That is, what do you mean by that? That is if f is continuous at a point, then it is not necessary that f must be derivable at that point. So if we have a f is continuous at a given point, then it is not necessary that it should be derivable at that point. So for this we need to give a counter example, right? So let's consider a function. Say, let me take a function f of modulus function. Say f of x is equal to modulus of x, and we will consider this at a point x equal to 0. Let's understand this. Now we have f of 0 equal to 0 because it is mod 0. This is equal to 0. Okay, now let's try to understand the left hand derivative and right hand derivative and the continuity. First, let's see whether it is continuous. So limit f of x as x is tending to say 0 minus. Okay, from the left hand side, this is equal to limit, this function is mod of x as x is tending to 0 minus. So as x is tending to 0 minus means what? It is from the left hand side. So therefore let me take this limit as from the left hand side means as x is tending to 0, your h tends to 0. So I'll be just changing from the left hand side means x write as 0 minus h. So therefore, because our x is 0 here, I'm replacing that by, as you're taking from left hand side. So as in the previous you have seen, if at a point C, if you're saying at a point C, if you're saying it is continuous, then you should put your x as c plus h. but here our point is x equal to 0. So therefore we have to write from the right hand side means it is 0 plus h, and from the left hand side means it is 0 minus h. Okay, if it is a point C, now since the point is 0 here, so therefore I have to put here 0 minus h. 0 minus h is nothing but what? Negative h. So as h is tending to 0, say plus. So this since it is a modulus function, this will be h. As h tends to 0, limit as h tends to 0, here let me write limit as h tends to 0, which will give me 0. Okay, now this is our left hand limit. Similarly, let me take the right hand limit. Limit of f of x as x is tending to 0 plus, this will be limit of modulus of x, because this is our function, as x is tending to 0 plus. I told you already, if as here our point is at x equal to 0, so point, in place of c I have 0. So my right hand limit means I should change our x by 0 plus h. So this will give me limit 0 plus h is nothing but what? H. Here as h is tending to 0 plus. So this will be, as h tends to 0, this will be what? 0. So here if you see, your limit of f of x as x is tending to 0 minus is equal to limit of f of x as x is tending to 0 plus, both are equal to what? 0. So here left hand limit exists and right hand limit exists, and it is also equal to f of 0. If I put, this is your 0, this is equal to f of 0. Why say f of 0? If you see f of 0 is 0, this is what you have got. So this is nothing but it is a continuous definition. So therefore the continuity holds. Hence we can say f of x is continuous. F of x is continuous. At what point? At x equal to 0. Now we have got f is continuous. Now we have to check whether it is differentiable. Let's check that. Now for that, what we do, let us take the left hand derivative. As I told you, we can also denote it by f prime of 0. This is equal to limit, by the definition of our derivability at a point, f of x minus f of 0, because at a 0 we are defining x minus 0. This is as x is tending to 0 minus, because it is a left hand derivative. Now this is equal to limit as x is tending to 0 minus, f of x is mod x. Let me write as mod x, and f of 0 is 0. By putting x equal to 0, this will be simply x, because x minus 0 is what? X. Now this is equal to, since here, as you know, mod x, by the definition of mod x in the first module, mod x is x if x is greater than 0, and it is negative x if x is less than 0, right? This is what we know. Now as it is x is tending to 0 minus, means from the left hand side x is less than 0. So your modulus of x is what? Your modulus of x will be negative x upon x. So this is limit as x is tending to 0 minus. So here this x I can cancel. This will be negative 1. Okay, this will be negative 1. And now let us take the right hand derivative. This will be limit f of x minus f of 0 divided by x minus 0 as x is tending to 0 plus, because from the right hand side. This is equal to limit, this function is mod x, this is 0, f of 0 is 0, and x minus 0, again it is x, as x is tending to 0 plus. As you know, modulus of x is x if x is greater than 0. Since our x is positive from the right hand side, so this value is x. So I can write this as x upon x, limit as x tends to 0 plus. This is what? This is 1. Now here it is negative 1, here it is positive 1. They exist. Since left hand derivative exists, right hand derivative exists, but they are not equal. Means left hand derivative at 0 is not equal to right hand derivative at 0, right? So they are not they are not equal. So therefore f is not derivable, at x equal to 0. Okay, so what we say, now we understood the given function, though it is continuous at a point x equal to 0, same function is not derivable at x equal to 0. So this is one counter example. So if f is not continuous at a, and again very important note, so if it is continuous, it need not to be derivable. And another important note is, if suppose you have f is not continuous at a, f is not continuous at a, it cannot be, it cannot be derivable at a. So this is very important. If it is not continuous, then it cannot be derivable. So this is also very important note. Okay, now let's try to understand with the help of some examples, the like how do we say that the given function is whether the given function is derivable or not. I think those examples we will see in the next video. For maybe in this video it is enough to understand the definition of a derivative and the property, how the derivative and continuity is related. And I think also we have seen the counter example to say this property, the continuity, I mean, and the derivative, how they're connected. If the function is derivable, then it is continuous. The converse need not to be true. And we have seen the example. I think this is all in this video. Maybe the next video we'll solve some examples and we will see how do we counter the derivative at a given point, whether it exists, whether it does not exist. All those examples we'll be discussing in the next video. So I think you can also generate some of the examples and comment in the box, guys, if you have any doubts, any difficulties. Okay, I think till then, take care, bye bye, see you in the next video.